Hello, BC Calc students. This is going to be your day 45 lesson on the fundamental theorem of calculus. If it sounds like a pretty big deal, it's because it is. It connects really our two worlds. I mean, we have our world of differential calculus, finding derivatives, and then we have our world where we take area under curves and integral calculus. So it's going to be a connection between those two major concepts, and we'll get to that in a little bit. But to review and recall what we've been doing over the past few days, we've got our formula for y average. Okay, the average y values that a function takes on the interval from a to b is defined as 1 over the length of the interval, b minus a, times the integral from a to b of f of x dx. So if you want to go ahead and practice this question, find the average value for y equals sine x on the interval from 0 to pi. We will go over this next time I see you. And then there's another practice question right below it that has to deal with average value. Find the average value of this function where it's positive, and then find the values of c that satisfy the mean value theorem. Well, this is a repeat from yesterday's notes. So I will leave this completely up to you. If you want to see if you can repeat the process for the same exact function and the same exact mean value theorem process, just to kind of see like where am I at with understanding mean value theorem as it relates to definite integrals, then certainly go back and try this one again and see if you can figure it out. If you get stuck, look back at your day 44 notes, which this question should be filled in at the very end, okay? But otherwise, I don't think we necessarily need to repeat that process right now. We'll do more mean value theorem and reference it a little bit in today's lesson as well. How about a little bit more Riemann in disguise? It's back, okay? So being able to express a Riemann sum as a definite integral. Remember, the whole goal here is we want to be able to separate this expression and start breaking it down into a function that represents the heights of the rectangles times the width. And that width part is always going to be 1 over n. So if you can separate a 1 over n, that's kind of a good goal to get started here. So the limit as n goes to infinity of k equals 1 to n. Well, if I separate 1 over n, that would leave me with the quantity n plus k over n times 1 over n. And then maybe simplifying this just one more step, it would be the limit as n goes to infinity of, from k equals 1 to n. This would be the 1 plus k over n times 1 over n. So you have a few different options from here. Once you have this set up, so we've got the heights of the function times the width right here, we want to figure out what definite integral represents the summation as the limit as n goes to infinity. So you can let your function x either represent the whole quantity here, 1 plus k over n, or you can just let x equal k over n. And we've done questions like this. I'm going to try and do it where I let x equal the whole quantity on the inside. It will make the integral just a little bit easier in the end to evaluate. Not that it would be more challenging, just let x represent this. But if I let x represent the whole quantity, let's talk about what the upper and lower bounds are on our integral. So the lower bound comes from when k equals 1. So if k equals 1, we get that this would be 1 plus 1 over n. So the limit as n goes to infinity of 1 plus 1 over n, well, as n goes to infinity, this goes to 0, so that's going to be a 1. And meanwhile, the upper bounds would come from when k is equal to n. So when k equals n, we're going to take the limit as n goes to infinity of 1 plus n over n, which since n over n is 1, we get limit as n goes to infinity here is 2. Which now if I go back to this statement here, this Riemann sum can be expressed as the definite integral from 1 to 2 of, now since I let x equal the entire quantity in the parentheses here, 1 plus k over n, I can say that this is x and then times the width dx. And because, again, I made that whole replacement here, it's just that much easier when I go to take the integral of x, which is x squared over 2. We now have our integral evaluation theorem, which allows us to plug in the upper and lower bounds and subtract those results. So we're going to get 2 squared over 2 minus 1 squared over 2. And 4 over 2 is 2. Minus a half would be 3 halves. Okay. So being able to pick this apart, break it down into, what is the function that I'm actually integrating here based on the heights on the function times the width. This is a skill that you'll see come up in homework assignments, and I'm sure on a quiz at some point in the future. So if you have any questions about this one in particular, let me know next time we are in class together. Let's talk a little bit about some average value applications. So we know what the formula for average value is at this point. And I want to show you how we can relate this to thinking about distance, velocity, and acceleration. So if I were to give you a distance versus time graph, I'll show you that right here. Okay. So in this distance versus time graph, we're looking at the time over the interval from 1 to 8 seconds, let's say, and this is the distance that is traveled. I might ask you for something like, what is the average velocity? Okay. And average velocity would just be, given this distance and time graph, this position curve, it would just be the slope of the secant line there. So to find the slope of the secant, usually S is our position, so that's why you'll see S's here. So S of 8 minus S sub 1 over the change in X, which is 8 minus 1. So that's my average velocity given the position function over here. And meanwhile, if I want the instantaneous velocity, we know that that's an application of a derivative, right? So that would be S prime of t. So that's how we've looked at this so far mainly, given a position function, being able to find velocity by finding derivatives. Certainly, again, average velocity would just be slope of the secant there. But what if I kind of work backwards from this a little bit, and I give you the velocity curve over here? Okay, so this is as time goes on, the velocity. So if this is our curve for time versus velocity, how would I figure out the average velocity over this time? Well, average velocity is now an application of the y average here. The average velocity over this time would be 1 over the difference in our interval, 8 minus 1, times the integral from 1 to 8 of v of t dt. So we have to now just think in the future, okay, if I want to find average velocity, given position, it's the slope of the secant, but if we already have velocity, the average velocity is the average of the y values, which would be our formula that we have at the top of the page here. Now, given this velocity function, instantaneous velocity would just be any v of t value, right? So if I want the instantaneous velocity at 4 seconds, if this is the velocity graph, I can do v of 4 and calculate that fairly easily, okay? So you'll see applications like this start to come up and sneak their way in as we explore integrals more and more here. Certainly some applications will make their way in. And there's other applications that you'll start to see involving something called average cost. So for example, the y average can be used to get the average cost of a gallon of gas over a year. So if you know as time goes on how the cost of a gallon of gas fluctuates over the time span of a year, you can figure out the average cost by thinking of it as an example of y average. Okay. So some good connections here that we're starting to make. Let's go ahead and take a look at what we have with our integration evaluation theorem at the top of the next page, right? So we know very clearly now that the integral from a to b of f of x dx can be found by doing f of b minus f of a. And again, that capital F represents the antiderivative of the function f of x. So make sure that we find that antiderivative, plug in the upper bound, subtract from when we plug in the lower bound. So we know that when we find the integral, that area under the curve, it's an accumulated area as time goes on. And this function in general, the integral from 1 to x of 1 over t dt, would look something like this to get started. Okay, so if we think about the function 1 over t, it's going to be when x is greater than 0, just this part of the curve right here. And we're integrating from a lower bound of 1 to an upper bound of x. So we're looking at any point, the area along the curve this way. So to find something like f of 2, based on how f of x is defined, f of x is the accumulation of area from 1 to some upper bound of the function 1 over t dt. So if I said, hey, let's find f of 2, it's the accumulation of the area from 1 to 2 of 1 over t dt. And the thing is that if I knew the antiderivative of this, I can use the integral evaluation theorem right up here. But we don't know this yet. Okay? Because if I use the anti-power rule and think of that as t to the negative 1, adding 1, now we get t to the 0 divided by 0, which is no good. So we, at this point, at least in our process, have to do math 9 from 1 to 2 of 1 over x dx. And it appears like the area from 1 to 2, the accumulated area for the function f of x here is 0.693 to 3 decimal place accuracy, so 0.693. So we can evaluate in accumulation functions pretty easily, right? Very similarly, f of 5 would be 1 to 5 is the upper bound now of 1 over t dt. And that's going to be approximately 1.609. Okay. So since f of x is just a function, we plug in our value of x. And what's interesting is we're not getting that y value that we're used to getting. We're getting an area as an output. It's the accumulated area underneath the curve. That's what's outputted for this function defined as capital F of x. Okay, so here's another example given capital G of x equals the integral from 2 to x of t squared dt. And again, we're only going to look at this right now for when x is greater than 0. If I said to find G of 3, we're looking at the accumulated area from 2 to 3 of t squared dt. Now, this is something that we know the antiderivative of, so we can use the integral evaluation theorem and say, hey, that's t cubed over 3. And if we plug in our upper bound and subtract our lower bound there, we'll get 3 cubed over 3 minus 2 cubed over 3. 27 minus 8 up in the numerator there would be an accumulated area of 19/3. Okay. Well, what's kind of interesting a little bit about this one is what if I asked you to do g of 1? So g of 1 would be the integral from 2 to 1, okay, t squared dt. And if you draw a picture of what we have going on here, we know what t squared looks like. Here's 1, here's 2. Here's the area there. But when we're accumulating area, if you're going from left to right, we think of the accumulation of area as being a positive amount. But what we'll find in this example is that as you work backwards, you're going to get a negative accumulated area. And you can justify that algebraically by thinking of this by using a little bit of integral properties that if you want to make it such that the bounds make a little bit more sense by having the upper bound of 2 and the lower bound of 1, we know that this is equal to the negated integral from 1 to 2 of t squared dt. So I can evaluate this integral right here and then negate my final answer. So we know that that's still t cubed over 3 from 2 to 1. So that's going to be 2 cubed over 3 minus 1 cubed over 3. So that's going to be 8 minus 1 is 7/3. Okay, but I have to negate that whole thing because of the negative we pulled out front when I reversed those bounds. So the final answer here is that we have an accumulated area of negative 7/3 when I calculate g of 1. So it seems like if you're just looking at this and you're looking at the shading, that the answer should come out to be positive because of where the area is located. However, when you work backwards, heading this way, the calculation is actually accumulating area backwards, and it winds up resulting in a negative accumulated area as justified by the algebra here. Okay. All right, so bringing this kind of all together here, if we look at this last example on the next page here, given capital F of x is the accumulation of area from 0 to x of the function t dt there. Well, if we think about graphically what's going on in this one, here's the function y equals t. And the area from 0 to x is going to look something like this. Okay. there's really two different ways to get your answers at any given moment. We can find the integral with respect to the original bounds, right? And then be able to use that as our new function to evaluate f of whatever we want, f of 2, f of 7, whatever we want to do. Okay, or if I said, hey, what's f of 2, you can just substitute in 2 for x and do that very specific definite integral. So we kind of have two methods at this point. So the two methods are, let's say method 1 is, let's do the definite integral with respect to these bounds. So the integral of t is going to be t squared over 2 with my upper and lower bounds of 0 and x. This is going to become x squared over 2. And then it would be minus 0. So the function f of x is really equal to x squared over 2. And you can confirm that on your calculator by going to y1 and y2 and comparing the following graphs. So in y1, you would look at the integral from 0 to x of, just make it x dx here. And in y2, we're going to look at 1/2 x squared. And we're going to see what the comparison is here. The only thing is what I'll say is when you type this into the calculator, it takes a little while to graph the integral. Okay, so don't be too surprised if when you hit graph, it takes a little longer than maybe you would expect. You can see it's really thinking hard up here about what it should be doing, but it's for every single value of x, graphing the function that represents this accumulated area here. So there we go. That's looking like 1/2 x squared to me. And what we should see in a minute is 1/2 x squared in red, copy right over the top of that. And let's see if that's true. Still thinking. Still thinking. All right, at some point it's going to switch over to, oh, yep, now I can see it. So the red came through and it copied right over the top. So these two things are equivalent. So if I said to do f of 2, well, that would just be 2 squared over 2, and 4 over 2 is 2. So one way is to find what the function is in general, define capital F of x, this is the accumulation function, and then just be able to evaluate it pretty easily. Or we can go back to the way we were just doing it a minute ago, which is if I said to find f of 2, find the integral from 0 to 2 of t dt. So that's still going to be t squared over 2, and then from 0 to 2, plug in those bounds, minus 0 squared over 2, and you still get 2 as an answer. So whether you want to define capital F of x in terms of x first, or just plug in the actual upper bound that you're given when you're evaluating something like f of 2, it really doesn't matter as far as how we get that answer. So just to practice with that concept, find f of 5 in two ways. Well, we can find in one instance the area from 1 to 5 of t squared dt. And the other way is to actually figure out what is capital F of x without writing it with our integral here. Let's take the integral of t squared dt and plug in the upper bound of x, the lower bound of 1. So what would f of x be? Well, f of x would be t cubed over 3, and my upper and lower bounds are x and 1 there. So this is going to be x cubed over 3 minus 1 cubed over 3, which is just minus a third. So the function capital F of x is represented by this. Okay, and you'll see when I evaluate the area over here, we're still going to have to take that integral and write t cubed over 3, and then we'll make the substitution of the upper and lower bounds here. So it's going to be 5 cubed over 3 minus 1 cubed over 3. So 125 minus 1 is 124 over 3. Meanwhile, over here, once you have your function defined, capital F of x as this accumulated area function, f of 5 is just a quick substitution in. And of course, we're going to get the same results when I plug in 5 for this x. So that's going to result in 124 over 3. Okay, just to make sure you're comfortable with both those ways, try this one where I ask you to calculate what f of negative 2 would be. Think about what the answer is going to result in based on what our upper limit now is for f of negative 2. And go ahead and take a look at that one. Okay. So we're finally at the point in the lesson where we get to talk about the major concept, the title of today's lesson, which is the first fundamental theorem of calculus. Okay. So here's what it states. If f is continuous on the interval from a to b, and f of x, capital F of x, is an accumulation function. That's why we were just looking at some examples of accumulation functions. Capital F of x is defined as the integral from a to x of f of t dt. If that's differentiable at every point x in the interval from a to b, then this is what we know to be true. df dx, d capital F dx, the derivative of the accumulation function would equal the derivative of this side that has the definite integral on it. And the derivative of the accumulation function winds up being the same as the original function f of x here. So with x as that upper bound, we know that the derivative of the integral gets you back to the original function f of x. And we'll get to a proof at the end of class today that, I don't know, we'll see how much time we have. Maybe we'll do that in the next video. Okay. But anyway, here's what we've got for some quick examples of what we got going on here. So if you take the derivative with respect to x of the accumulation function here from negative pi to x of cosine of t dt, according to the first fundamental theorem of calculus, this is equal to cosine x. Done. And I'll tell you, it doesn't really matter what that lower bound is. Okay, so in general, it's a here. If it's negative pi, the reason why it doesn't matter the lower bounds is because the derivative of a constant is 0. So I can put whatever I want here, and the derivative with respect to x, as long as x is the upper bound here, is just going to be cosine of x. And if you're unsure, go ahead and evaluate this definite integral with respect to that x, and then take its derivative and see what happens. In fact, we could do that pretty easily. The antiderivative of cosine of t would be sine of t. So I want to do the derivative with respect to x of sine of t with the appropriate bounds of an upper bound of x and a lower bound of negative pi. So there's going to be the derivative with respect to x of the upper bound would be sine x. And then I'm going to do minus sine of negative pi. Now you can do this in one of two ways. You can do the derivative of each, right? The derivative of a difference is equal to the difference of the derivatives. Or we can evaluate this quick, because sine of negative pi, by the way, is 0. So this would just turn into the derivative of sine x, which of course is cosine x. Same exact thing. So if you're a little untrusting at first of what the first fundamental theorem of calculus says, you could actually go through the process of evaluating the integrals as long as you know what the antiderivative is. Plug in the bounds, find the, I mean, it takes a lot longer than just knowing that this is what the first fundamental theorem states. Well, of course, you would run into a roadblock with the next one. We don't know the antiderivative of 1 over 1 plus t squared. What I do, however, know is if I take the derivative with respect to x of this accumulation function from 0 to x, that the result would be 1 over 1 plus x squared. It would be the function f of x. And that's it. It's as easy as just plugging in an x for t. Okay, so this does get a little different depending on the bounds at times, but we'll get into that in future lessons. Same thing here. I mean, this is getting fairly complicated. We have no idea what the antiderivative of this is. But if I'm taking the derivative of this accumulation function, it would be secant of x over radical x times e to the x. Done. Okay. On the next page, if f of x is equal to the accumulation function e to the sine t from the bounds from e to x, find f prime of x. Well, according to the fundamental theorem of calculus, f prime of x, the derivative of the accumulation function would be e to the sine x. Done. Boy, you're going to like if that's a multiple choice question. Okay. And there is a little bit of a fun fact here. The fun fact is that although I can take the derivative of this accumulation function, there actually is, not every function has an antiderivative, and this is one of them. There is no antiderivative for e to the sine t dt. So that's weird that we may come across functions in the future that really just don't have an antiderivative, and that's one of them. However, the first fundamental theorem of calculus still is applicable, that if I take the derivative of this accumulation function, we get to the function e to the sine x. Okay. So the proof of this fundamental theorem, I'll go through it right now. If you want to kind of save this and save it for another day, of course, that's fine. But just to kind of justify quickly why this is the case, you need a diagram that looks something like this in your notes. Okay, maybe I'll recap this next time I see you guys in class anyway, but we're going to try to justify here how the derivative of the accumulation function just gets you back to the function f of x. Okay, so once you have that diagram copied over, and I'll explain what all this means in a minute. So given an accumulation function for the function f of t up there, the accumulation function I'm defining is from a to x of f of t dt. And I'll show you why we have that x plus delta x in a moment here. Okay, so accumulation function, area under the curve there. The fundamental theorem of calculus claims that if you take the derivative of the accumulation function, you're going to get f of x. So that's what we're going to try and prove using the limit definition of a derivative. Okay. So here's what the limit definition of derivative would say. We're going to take, that's why we have this delta x here. If I go and add on x plus delta x here, the limit as x or delta x goes to 0 of f of x plus delta x minus f of x over delta x is what we're working with here. So this is the limit definition of derivative, right? Definition of derivative. Okay. Well, because we're using capital F in this case, these are both accumulation functions. So since there are these accumulation functions, we can replace it with this notation in the next step by doing the following. So we have some accumulation functions. Okay, so f of x plus delta x is the accumulated area from a to x plus delta x for the function f of t dt. And capital F of x was defined earlier as the accumulation of area from a to x of f of t dt. Now here's what's going to get a little bit weird. I'm going to combine these into one integral. But the way I'm going to do that is if you reverse the bounds here and make it go from x to a, then this integral will get negated out front, which would make that a positive. So if you switch the bounds and you make this go from x to a, if this goes from a to x plus delta x, adding those integrals together, because again, this is going to become positive when I negate this by switching the bounds. Adding those integrals together would make the total integral here go from the lower bound of x to the upper bound of x plus delta x. So it looks like some magic happened to get to this next stage in the process here, but this is just properties of integrals. Switch those bounds. This is going to turn positive now. And if you're adding the integral from x to a, and then from a to this upper bound, you can add those together and go from x to x plus delta x. Okay. So that brings us back up to the picture for a moment here, and you look at x plus delta x, okay, that accumulated area here. Why do I have this value c in here? Well, remember that the area under this curve, at some point in the process, there would be a value c such that the y average there at c is equal to the area under the curve. So that's maybe sounding familiar as some mean value theorem. So what would the mean value theorem state? Well, the mean value theorem would state that that area is equal to f of c times the length of that interval. So what's the length of this interval? It's delta x. So at the end of the process, you can see we're starting to wrap things up right here. This is the mean value theorem for definite integrals. That this is going to become f of c times delta x. Oh, hang on.
Good morning, Fairmont High School. Today is a B day.
Apparently today's a B day. Who knows what it will be in the future? But so this last step, that's why we get to replace that whole thing with f of c times delta x right there. It's from the mean value theorem. Check it out. So when I have that over delta x, those delta x's cancel. What's the limit as delta x goes to 0 of f of c? Well, as delta x goes to 0, c is going to go to x. So therefore, in that last stage, we have now shown that when I take the limit as delta x goes to 0 of f of c, that we do wind up with f of x in the end. And I know that there's some tricky parts to this derivation here and in this proof here, but it is a solid proof to show that the fundamental theorem of calculus holds true. When you take the derivative of an accumulation function, you get f of x as a result. If you have any questions about that next time I see you, of course, you'll let me know. Otherwise, have a great rest of your day. Today is some sort of B day here. We'll see you guys later.